In this example, we're told we have a gas within a piston cylinder assembly, so let me go ahead and sketch that out. So here's our cylinder, here's the piston, we have some gas in here, and it undergoes a thermodynamic cycle consisting of three processes. So process 1 to 2 is compression with constant internal energy, PV equals a constant. We'll come back to that in a moment. Process 2 to 3 is constant volume cooling to a given pressure and volume. And 3 to 1 is constant pressure expansion, where the total work acting on the piston in this process is given. We're told for the cycle, the net amount of work done by the gas on the piston is minus 8.3 kilojoules. That means that the piston's doing some work on the gas. There are no changes in kinetic or potential energy, and we're asked to sketch the processes on a PV diagram and then some other things here that we'll get to in a little bit. So my system here is going to be the gas. And there's going to be some heat transfer going into the gas, and the gas doing some work on the surroundings. Let's start with the PV diagram. So here's pressure on the vertical axis, volume on the horizontal axis. We're dealing with a gas, so there is no vapor dome. Process 1 to 2 is a compression with constant internal energy, PV equals a constant. This is a polytropic process, where the power exponent n is equal to 1 here. And so that's a hyperbola. You can see, if PV is equal to a constant, then P is equal to a constant over the volume. So that's like a hyperbola, so it'll look something like that. And since it's a compression, that means that the volume is getting smaller. So we'll start with 0.1 over here, and then go to 0.2 over here. So we're going that way. Okay, so let me go ahead and put in something. Here's volume at 1. Pressure at 1 is right here. And then, let's see, pressure at 2 is right here. And here's volume of 2. Okay, so that's the first process, process 1 to 2. 2 to 3 is constant volume cooling to a pressure of 140 kilopascals and a volume. Well, since it's constant volume, V2 and V3 will be the same, and we're given that that's 0.028 cubic meters. And since it's a cooling process, the temperature is going to drop, and that means that at constant volume, that means the temperature is going to drop the pressure is going to drop as well. So we're going to go down this way. And I know that process 3 to 1 is constant pressure expansion, so that means that the pressure at 3 should be equal to the pressure at 1. So 0.3 is right there. And so from 3 to 1, it's a constant pressure expansion. Expansion means that the volume's increasing, so we're going that way. Since we're told process 2 to 3, it's constant volume cooling to a pressure of 140 kilopascals, that means that P3 is 140 kilopascals. So P3 and P1 are the same. And so I think that covers our whole PV diagram. So this is the process. We start here, we go through this polytropic process. We do a compression from 1 to 2 following that polytropic process. 2 to 3 is constant volume process. The pressure is going to drop there. We hit state 3, and that's constant pressure expansion to that point. And let me just talk a little bit about this constant internal energy statement here. So we're not explicitly told we're dealing with an ideal gas, but since we're dealing with a gas, it's pretty reasonable to assume that. We know from the ideal gas law that PV is equal to mRT, and since PV is equal to a constant, that means that mRT is equal to a constant, right? Well, the mass, of course, is going to be a constant since we're dealing with a system. Gas constant's a constant, so that means the temperature should be a constant. And we know for an ideal gas, the specific internal energy is a function only of temperature. So if PV is a constant, and that means temperature is a constant, which means that the specific internal energy will be a constant. So that's where we get this constant internal energy term from there. And then the reason I knew that the pressure decreased from 2 to 3 with constant volume cooling is if, again, thinking about the ideal gas law, If it's constant volume, the V is a constant. Of course, M and R are constants. If it's cooling, the temperature is going down, so that must mean then that the pressure is going down. So that was the logic I used to draw 0.3 below 0.2. Okay, well, let's continue. So we've done part A, sketch the processes on a PV diagram. Let's do part B, determine the volume at state 1. So we're trying to find this volume right here. So I'm trying to think about what information I have to connect to state 1 here to find its volume. Well, I know the pressure, and I know the pressure actually from 3 to 1 is a constant, and I know this volume, and I'm also given the work. If you go back up here, you'll see that the work in process 3 to 1 is 10.5 kilojoules. So I know that that work is PDV work, so that's going to be related to the volume at 1. So let me write that out. The work done by the gas on the piston as I go from 3 to 1 is PDV work, as the volume goes from volume 3 to volume 1. And I know that pressure is a constant, so this will just be P times V1 minus V3. And when I look at this, I know this information. I know the work that was given is the 10.5 kilojoules. I know the pressure, that's 140 kilopascals. V1 is what I'm trying to find, and V3 is given, 0.028 cubic meters. So I should be able to find the volume at 1 from the work expression. So I can solve that then for V1. And when I do that, that comes out to be 0.103 cubic meters. Okay. By the way, that work, just graphically in the picture, that's the area underneath the path in the PV plot, right? So again, on a PV plot, the integral PDV is just the area under the path on a PV plot. So it's just that green area. The green area is equal to this value. So that's what it looks like graphically. Okay, now we're asked to determine the work in heat transfer for process 1 to 2. So let's focus on the work for process 1 to 2. That would graphically, let me erase this one, graphically that would be the area under this curve. Okay, so the work from 1 to 2 will be that green area. By the way, I just calculated the work in this region, right? That's that 10.5. I mean, I was given that. So if I'm going to find the work on the green shaded area, that work from 1 to 2, I could just, I should be able to get that from if I know the work over the whole cycle, which I'm actually given right here. Let me highlight that. I'm told that the work over the whole cycle is given here. So the work over the whole cycle would be, let me see if I'm running out of colors here, but it'll be this kind of orange hatched area here. Right, so the work over the whole cycle would just be the area inside the cycle. Okay, so if I know that orange work and the blue work, I could just add those together to get the green work. So mathematically, it looks like this. So the work over the whole cycle will be the work done going from 1 to 2, which is what I'm trying to find, plus the work going from 2 to 3, plus the work in going from 3 to 1. Okay. And then we know that the work done from 2 to 3, right here, this constant volume process, that's going to be 0, since V2 equals V3. Work 3 to 1, that's given, that's the 10.5 kilojoules. And I'm also given the work over the whole cycle is the minus 8.3 kilojoules. So I then can solve for the work done by the gas from 1 to 2. And if you plug in those numbers, it comes out to be minus 18.8 kilojoules. So This is kind of the mathematical way to do it. The work over the whole cycle would be the work done in each set of processes added together. And just noting that the work from 2 to 3 is 0 because the volume is the same. Graphically, it's just like what I talked about up here. The work done by the whole cycle is this orange hatched area. It's just the area inside the cycle. The work done from 1 to 2 is the green shaded area. 2 to 3, I'm not showing it on here because it's vertical, there is no work. And 3 to 1 is the blue hatched area. Okay, so if you take the so the green area would be the orange plus the blue, which is we have to be careful. Let me take that back. It's not the orange plus the blue. The reason I have to be careful is the signs. The blue area is positive because we're doing an expansion, so that would give me a positive work done by the gas. The green area is actually negative, as you can see that here, because when going from 1 to 2, we're going off to the left, and so that ends up giving you a negative area. Okay? And so they have to be a little careful with that. It still works out graphically, but you just have to be careful of the signs. Okay, so anyway, we found the work now from 1 to 2. We still have to find the heat transfer for process 1 to 2. So the way we're going to do that is we'll just go ahead and let's apply the first law from 1 to 2. And the reason I say that is because we know from 1 to 2 we're told that we're dealing with a constant internal energy. So that implies that the first law would be useful. So the change in total energy from 1 to 2 is going to be Q into 1 to 2 minus the work done by from 1 to 2. And we're trying to solve for the heat transfer. The work done by 1 to 2, we just calculated that. And this will be the change in, so the change in total energy is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. And we're told in the problem statement that we can ignore changes in kinetic and potential energy. And the change in internal energy is also 0. That's actually given up here in the problem statement. It's constant internal energy. We reason that through some ideal gas arguments. So what we see then is that the Q into the gas in process 1-2 will be equal to the work done by the gas from 1 to 2. And so that will be minus 18.8 kilojoules. Okay, so that's how we determine the heat transfer from 1 to 2. So that takes care of that. So we've done all 3 of those. The next question is this a power cycle or a refrigeration heat pump cycle? Explain. So the picture I have in mind for that is this. So we have kind of the classic picture of a hot reservoir, our system, and a cold reservoir. Some heat going in to the system, heat being removed, going out of the system into the hot reservoir, and then some work. Now, here our system is the gas. Let me go ahead and put it's the gas piston arrangement. And the difference on whether this is a heat pump cycle, refrigeration cycle, or, so heat pump, refrigeration cycle, or a power cycle is just the direction of the work here. Is the work going, if the work is coming out of the system, then I know it's a power cycle. If it's going into the system, then I know it's a refrigeration or heat pump cycle. And since we're told that the net amount of work done by the gas on the piston is negative, that means that there's work that's going into, so there's work being done on the system over the cycle, right? So, because this is the work done by the gas on the piston. So we're told that this, which just means that the work done on the system over the cycle is positive. right? So that means we have some work going into our system, which means it must be a refrigeration or heat pump cycle. So I'm just writing it out here. So that was the logic to determine that it's a refrigeration or heat pump cycle. Now, one question would be, is it a refrigeration or a heat pump? Do we know, can we determine that? And we can't really figure that part out. We don't know whether it's a refrigeration cycle or heat pump cycle. The two cycles actually look the same. It's just what the objective is for a refrigeration or heat pump cycle. For a refrigeration cycle, you really want to cool down the cold reservoir. For a heat pump cycle, you want to heat up the hot reservoir. Or the goal is to put, I shouldn't say heat up, I should say you want to remove as much energy as you can from the cold reservoir for a refrigeration cycle. You want to put as much energy as you can into the hot reservoir for a heat pump cycle. But we can't really tell what the purpose of this system is here. So we can't differentiate between refrigeration and heat pump cycles. All we can do is say that since there's work going into that system, we know it must be one of these two. It's certainly not a power cycle because we're not extracting work out of the system. We're putting work into it. Okay, so just to recap on this problem, it's kind of an unusual problem, but it's a matter of using finding PDV work, being able to recognize how to draw the different paths on a PV diagram for the cycle, how to calculate PDV work, recognizing that the total work over the whole cycle is the work done in each of the processes, and then making use of the first law, and then the last little bit, is it a power refrigeration cycle? It's just sort of recognizing is the work going into or out of the system, and that kind of a plot. Okay, we'll end the example there.